Case 1. Coming off of the ground, we've got 2 supports and a 600-pound weight. And so the first thing we've got to determine, which we looked at in the introductory video, was are both of these supports supporting in an upward direction, or is one pushing in an upward and one pulling in a downward direction in order to sustain the weight in a stationary position. We found that both of these were supporting in an upward direction in order for that weight to stay in place and not move. So when we go to make our scale drawing will not look like that original drawing. We will start with a baseline, a horizontal baseline, and we'll look at that and notice that both of them are moving up. So we can start with that line being towards the bottom of our drawing space. No particular length, but we do want to have a center point to work off of. Now we've got to figure out which of these two. Does it appear that if you look at this as being the origin where that vector starts, which of the two of them is going into quadrant 1? That's going to be our first vector, our vector A. And if you can tell, this one's going into quadrant 1, and this one looks to be going into quadrant 2, the way it is moving. So we'll call this one vector A and this one B. Okay. So I'm going to draw vector A at an arbitrary length of 8 centimeters. The only reason I've chosen 8 is because I've done enough of these and I realize that 8 is a length that fits well on the paper, and everything scaled to that seems to fit well on the paper most of the time. So we'll draw it at 8 centimeters. However, the first thing I'm going to need to measure out is the angle.
Make sure it's lined up.
You can see where the 0 right here is lined up, and make a mark of 51 degrees. I'm going to connect from that center point through that angle of measure 8 centimeters. Precise the measurements,
The more precise our estimate will be.
This is A. I've drawn it at 8 centimeters. I have an angle measure of 51 degrees. What I'm going to do next is to make a right triangle out of this. And so I simply need to turn my protractor upside down, put the center point on the end point of vector A, line this up with 51 degrees by that alternate interior postulate, and then make a mark at 90 degrees. Connect from the end point down to that baseline, and that should be close to 90 degrees. Now, something I did not bring up earlier, but it's very important to this entire idea, is that if you'll think about any of these, regardless of ground case, wall case, 1 or 2, all of them have the same thing. A and B have forces that are moving in both an X and a Y direction. All of the ones that we will do will not be vertical or horizontal, they'll be at an angle, which means that there is some X to this support, but there's also this vertical aspect, so there's some Y direction to this support for both A and B. However, for the weight, it is always moving straight down no left or right to it, straight down, which means it only has a y direction for its force. Here's what we like to say, that the sum of the forces in the x direction, in order for this weight to not move, which is the whole idea of statics, for it not to move, those forces have got to be 0. The same for the sum of the forces in the y direction. Sum of the forces must be 0. If you have more x pushing in a particular direction, it is going to cause that to move. If you have more x moving in the left, then it's going to move to the left. If you have more y direction moving downward, it's going to cause it to move downward. So the sum of the forces in the x direction must be 0. The sum of the forces in the y direction also must be 0. Now we've determined that only A and B have an x direction, but A, B, and the weight all have a y direction. So knowing this, we're going to measure these two. This is going to be our A in the y direction, it's the vertical. This is going to be our A in the x direction, and it's going to be the horizontal force of vector A. So we'll measure it out in centimeters, be as accurate as possible. Again, accuracy will make the estimate much more accurate. I'm measuring this as 5.1 centimeters. My vertical measurement appears to be 6.3 centimeters. So there's talking about this first vector A. Now we're going to scale draw vector B. Well, the one thing we know about vector B, it's going upward, it's going towards quadrant 2, this area. We're going to start it at the same center point. So I'm going to measure the angle of 44 degrees from that center point. Make sure I'm lined up again. 44 degrees from the baseline. There's 44 right there. I'm not going to have a measurement to it just yet. I'm actually going to have to go off of the fact that the only two forces with an x direction are A and B. And in order for that to become 0, you'll notice that x for A is moving towards the right, and x for vector B is moving to the left. They're moving in opposite directions. In order for this weight to stay in place, those two have got to be exactly the same. This one cannot be more than the x direction of B, or it will pull it to the left or the right. So for a scale drawing, I've got to draw my B, x direction of B, to be equivalent to A. So I've got to measure it out to be 5.1 centimeters, as accurate as I can get. And that's how we'll determine vector B. I've got its angle. I'm going to have to connect it to this. This is also going to be a right triangle. So I'll take my protractor, line it up here, make the measurement for 90 degrees. I can go on and even connect that if I want to. Doesn't matter if you overdraw it. And then I'm going to also connect the measured out 44-degree measurement here. To form my vector B. This is B in the Y direction. And so now I'm going to need to measure those out to see what they came out to be. Vector B itself, looks to be 6.9, really close to 7. Actually, I think it is 7. And B sub Y, .8 centimeters. So now we've got our scale drawing completed. We've got to go ahead and make our calculations, our scale drawing estimate. So I know that A is equal to 8 centimeters, A sub X 5.1, A sub Y 6.3 centimeters, B was 7 centimeters, B sub X, of course it was the same as A sub X, so it's 5.1, and BY is, what did I measure that to be? 4.8 centimeters. So we're going to take this scale drawing, and what we're going to do is make a scale for centimeters to pounds. Now, we mentioned this earlier, but the weight only has Y direction. What do we notice about the weight, the direction of the weight? Its direction is pulling downward while both A and B's Y direction is moving upward. So these two A and B Y directions are combining to oppose the weight's Y direction. These two are pulling upward against or opposing the weight which is pulling straight down. Therefore, the A sub Y and B sub Y, the Y directions of those two vectors, are working together to equal this 600 pounds. So we will say, to get our scale, that 6.3 plus 4.8, these are centimeters, is equal to 600 pounds. And in order to make my scale, I need to add that up, which gives me 11.1 centimeters is equal to 600 pounds. And I want to know what 1 centimeter is equivalent to, so I'm going to divide by 11.1 on both sides, so that I can get a scale of, for every 1 centimeter is approximately how many pounds. So I'm going to just divide 600 divided by 11.1, and I find that every centimeter to scale is 54.05 pounds. And so our ultimate objective is to find out how many pounds of stress are on the actual supports of A and B. And so I'm going to multiply that by our scale. And I get 432.43 pounds of stress being placed on A, and then I'm going to
multiply that same number and get an approximate amount of stress being placed on B. So our answers, amount of stress being placed on A is 432.43 pounds, and on B is 378.38 pounds. Their sum, if I added them together, does come out to be greater than the 600 pounds, but you have to consider that they are at angles, and so because of that, they're not pulling straight up, and so it would not be exactly 600 pounds.